Alrighty. So for this first part, really, we're just going over Diels-Alder, just understanding which dienes can react and which ones can't. And so it's important to remember that you need cis double bonds in order to do Diels-Alder. And so certain sigma bonds can rotate, and the rotation of those bonds is actually what enables us to do Diels-Alder with them. So for like this one, I'm not pushing electrons there. I'm like twisting the molecule. And so if the molecule is involved in a ring, a lot of times it can't. So like this right here is locked. So it can't react. This guy over here also locked because basically the double bonds inside the ring, ring torsion prevents any kind of rotation. Whereas over here, it's pretty easy to just rotate. Think of these single bonds as things that can spin back and forth, um, and that helps. Even if it is on a ring, if they're two different rings, they can still swing over and come together. Not crap. Um, so then we've also got steric hindrance. And so steric hindrance for Diels-Alder is really pretty simple because there's only 2 or 3 things that can prevent um, things from reacting as far as like if they're in trans and then locked in trans positions. And so that's like if it's in a ring, if you've got a T-butyl group, which is one of these. So if one of these T-butyl groups are on either side of this, um, it usually prevents the other side from twisting back. And it'll be really obvious. I doubt they would do like one T-butyl group and one not. But yeah, over here, same thing. This might not necessarily be a T-butyl group, but it's on a ring, and so there's 3 carbon substituents on that carbon that's engaged in this double bond. So you're looking at those bonds. And if any of those bonds are T-butyl group, so it has nothing but carbon-carbon bonds, you'll know that it's going to be sterically hindered. And so does that concept make sense? Okay, that's a nod. That's good. And really that one shouldn't be what's hard here. I think in my opinion with this Diels-Alder stuff, the hardest part is just drawing it. And so for me, I really like to draw the transition states. And so for that, you have to kind of draw this dotted arrow and then draw the electron movements. It's important to remember that once you're over here, this is planar. So nothing can be on dashes or wedges on any of these carbons, because if this is an sp2 carbon, that means it's all on one plane. Everything's involved in that bond. It's all just coming off of it. Does that make sense? Cool. And so, yeah, once again, this one is also planar. So really what you've got here is you've got like 2 different planes, and they're intersecting to form like a plane in the middle. So you've got these 2 guys right here. They're coming together to make this guy right here. And you'll still have kind of like what my fingers are doing off on the side. Unless you reform that double bond and then everything is on that same plane. And stuff over here, because this is still sp3, sp3 carbons can still have dashes and wedges. So make sure you're looking for those double bonds, because those double bonds will prevent stuff from being on dashes or wedges. Yeah. For this next guy, same deal. We've got the transition state here. You don't have to redraw it or anything because you're not doing any kind of flipping and spinning. And the dienophile for all of these is always on the right. The diene is always on the left. So yeah, kind of gives you that one just in the organization of it. And so for this one, you'll notice that it's in trans. And so one's here and one's there. And so when this plane comes in and hits it and makes this flat plane right here, there's still going to be one going up and then one going down. Or actually, they'll just be on the plane. So one will be coming towards me and one will be going away from me. But they'll all still be on the same plane. There's a video actually on this that Khan Academy, I think, did, where there's a guy with a model kit. and he actually like goes over the endo and exo rules of this stuff. And if you're having trouble visualizing this, it's really important that you are able to like have some spatial understanding of this concept. I'd recommend going back and watching it. I think that was on March like 17th, or no, March 25th, something like that. It's in like one of the supplemental contents from a couple days ago that I actually like described where everything was. But anyway, so for this last one, once again, we've got to redraw it because we're spinning the molecule. You'll notice this is a triple bond. Triple bonds are just, they're planar, just like the other ones. And they're going to stay planar all the way through. So this should not be on dashes or wedges. And yeah, it's important to remember that this bond, you form a double bond over here. But yeah, that's all there is for that. Any questions on that first part?
And these are racemic, correct?
Where?
Those that you just did.
So this one's not. That one, there's only one product because it's all planar. Well, all this part is planar. For this one, yeah, it is racemic. Well, technically, each of these carbons are racemic. It could be either way. And then for this one, really because you have symmetry, that's a meso compound. Or is, well, actually, I think a meso compound would be if this was on wedge 2. So these might be considered racemic as well, but they won't really ask you on that about racemic. You do need to remember that endo and exo versions of these molecules are not enantiomers. Those are diastaminers. So diastaminers are just any kind of stereoisomer that's not an enantiomer. And you'll get into all different types of stereoisomer relationships in biochemistry with sugars and stuff like that. So it's important that you have a grasp of that stuff. This next stuff is just a matter of drawing. I think the hardest part of this is just drawing these. If you go ahead and put your two carbons right here, like on a line, it really helps to draw the rest of it. I think the hardest carbon is to draw this one in the back. So if you start with that one in the back and then just kind of draw one up and one down, that usually is a good way to do all three of them. Just from those, drawing these first two and then like from that. But yeah, it's important to remember these bridgeheads are coming up at you. Basically, you've got like a flat thing here, and you're always going to want to go to where the bridgehead is going up. And so you're going to work under the molecule. Bridgehead will pop up, and that's basically the epitome of the endo rule. And the endo rule is a lot less complicated than I originally thought. I didn't feel like I understood it when I first took the class, but that Khan Academy video really kind of es muy bueno. Anyway, so once again, we're doing bridgeheads on this one. This is one carbon in the middle that is coming together across the two sides of the ring. And so this guy over here, you want to make sure that, like I said, you've got the frill coming up, and then this other thing is attacking head on. So it's hitting it like this, and then it's just sticking there like this. And you can think of it as it's a lot easier, and you want to keep your head up. I just think of it as like when you're going, you want to keep your head up when you're doing these reactions. And so then you're going to work under the hood. And so, yeah, there's also like an analogy Dr. Nichols really likes where you describe it as like you don't want to back into a garage. So you don't want them to like try and lay back into each other. It's a lot easier to go head first into a garage. So if that helps you, that's another way of thinking about it. Once again, all the dianophiles are on the right. Dienes are on the left. Um, and so this next part, the dienes are on the left again, dienophiles on the right. Um, Once again, it really helps to draw the transition state. Um, for this one especially, it's kind of an ugly looking molecule. And an important thing to remember to make sure you're following endo and exo rule and all that kind of stuff is make sure that you have your hydrogens on wedges. So when the hydrogens are on the wedges, it shows you that whatever's the rest of the molecule is going under it. Um, so that's important. And so for this one, really, we've got two flat guys coming in. You've got one that's reacting, and then this other guy. So here's like the double bond is going to react directly. And so see, I'm putting my head up, and then I'm attacking head on. And so down here, my fingers are the two ketone groups. And so you're going to have up here the bridge head is on my index and like ring middle finger. The rest of my hand is this molecule over here. And then, yeah, you're forming this part of my hand. That's the other ring you're forming. And then the bottom, the base of my hands with my two fingers are the ketones and the ether there. Um, so those are like kind of like an ester ring thing. So yeah, and that's pretty much all there is to know about this stuff. Um, Drawing it is kind of hard, but once you have seen it in a model kit and you've played with it some, uh, this stuff gets really easy. I think this is probably the easiest stuff we do. Um, yeah, so this is the very last. This is a challenge problem. If you guys don't have any questions, then y'all are good to go. But everybody do all three of them. And just a kind of little helpful reminder, uh, that's one ring. So be looking for those. Take it away.
So yeah, this one had said that there was 1 mole of diene, 1 mole of that one. So your diene had to have kind of like this part, like if you kind of cut this in half, it has to have all of this because it said 1 mole of diene, but if it was 2 moles, you could have done like what was over here. And then I just numbered these, and like this double bond goes over here, makes that. This one, like the 4 and 5 carbon bond and the 6 and 1 carbon bond, and then you get that. Kind of similar over here, but it's 2 moles, so like it's basically just a butadiene on both sides, and the same thing happens on both sides, and you get that. And this one was kind of confusing for me, but it's just a cyclohexane with a methoxide on it, and kind of same thing that happens is that goes over there, that goes over here, 4 bonds to 5, 6 bonds to 1, and these 2 carbons between the 1 and 4 will be like these because they're still there, they can't go anywhere, so it's kind of like above everything else.
Yeah.
Good enough explanation?
Yeah, that was perfect. I mean, that was everything that I would have covered, and perfect. Make sure you remember that those two cyanide groups are on the same plane. And I mean, aside from that, like that was everything for this one. Great job, Sale.
Thank you.
Yeah, I'll go ahead and throw it up, and then if y'all have any questions, we can go over those. But I mean, we still got 5 minutes left, and that's all. So, yeah, basically everything that he said. I went ahead and annotated it. I put blue for bonds that were created, and then also I did the green highlighter for new benzene rings or not benzene rings, new cyclohexane rings. And then it's important to remember that those two cyanide groups are on the same plane because, like I've been saying, um, if you've got a double bond, all the substituents of that double bond are on the same plane. So remember that. And yeah, other than that, I mean, great job, guys. Did y'all want to talk about steric hindrance for a little bit?
Yeah, sure.
Okay. So that's kind of coming back up to here. And so for the ones that they're going to do it, because steric hindrance obviously exists on a spectrum. Some things are more hindered than others. And so for these at least, unless it's a trans and locked in trans by steric hindrance like this, consider it as it's going to react. I know you can do a lot with these as far as like just the spatial awareness goes. But really, let's find one that looks like it would be pretty sterically hindered. I felt like these were kind of busy. Like this one, I thought was pretty busy. Despite having all this stuff going on, and this stuff going on, all this reaction will still happen because these guys are going to find a plane of where they can create a new double bond. And so this stuff is really kind of sneaky because it you don't have to worry too much about steric hindrance as far as stuff being on these groups or being over here. I guess if you did come across something where you had a T-butyl group right here, and then another, so like this, and then I guess like, but even then, oh, that's wrong. It's going to be pretty hard to fully hinder this reaction. You more or less need to worry about the formation of the dienes of the dienophiles. So I wouldn't worry too much about steric hindrance in the dienophile and diene once you're for sure they are a diene when they are a dienophile, about it preventing the reaction from happening.
So like when you said that even though those T-butyls that you just added like are on there, the reaction can still happen, but why in like part B, the ones with the T-butyl can't do the reaction?
So the problem with the part B thing was these guys are in trans. It's a difference between trans molecules and so like this isn't even these aren't even dienes or dienes. They aren't cis dienes. You have to have a cis diene. So you can lock something and sterically hinder it away from being able to get into the cis diene conformation. But once you know you have something in the cis diene conformation, it's going to be able to react pretty consistently. And I'm sure steric hindrance can slow things down, but it's less of a factor. And it's not something that they really throw at you too much. Does that make sense?
So these ones, like you can't do resonance structures to make it cis, or I don't know if resonance is the right word, but
Yeah.
you can't like rotate it around to make it cis, but with the other ones you can.
Yeah, because what we're doing with all those other bonds, we're taking this bond right here and we're twisting it. So like originally it was like my hand, my thumbs are the two like trans molecules, and we're just twisting it up. But if something is right here and blocking it, I can't twist. So if something prevents me from being able to twist, then I'm locked in this position. And as long as the molecule is in this position, it's not going to be in an orientation where it will be able to react. Does that make sense?
Yeah, thank you.
For sure. And so yeah, that's kind of the premise here. But once you're in that position where you have the two dienes, or the diene and then the dienophile, steric hindrance plays a lot less of a role. So yeah. That's not to say it can't. But chemistry is weird. You never want to give like a hard every time rule, because you can usually find a way to manipulate it where it's not true. But anyway, if you guys have no other questions, I mean, this is it. We're finishing still 2 minutes early. Yeah.
But I had one more question of how you figured out that the dienophile was a triple bond instead of a double bond again.
For sure. So for this one, usually when you form a diene, or you form a new ring, you'll notice only the diene side of the molecule is the one that has the double bond in it. And so we've got this guy here, these guys will go here, and this guy will go here. And so that leaves only one double bond in the molecule. So if the new ring has a second double bond, that double bond has to have been there from the dienophile. And so in those circumstances, you'll have a third bond in the dienophile. Does that make sense?
Yeah, I think so.
So like we'd be throwing in this, and this. You can't really see that very well. This and this.
Oh, okay. And then there would also be like the little arch above too, along with it.
So for this one, if you wanted to have an arch, you would have to do that. So here, 1 second. Let's kind of clean things up here. Like that, because these two carbons are going to be what would form the arch. Oops. Does that make sense?
Yes.
So you could form them with the arch like that by having the diene with that. And then also you could include a double bond here if you included a triple bond here. That makes sense?
Yeah, I think so. So I'm looking for 2 double bonds in the product.
Yeah.
Okay.
And that'll look, drawing that will look ugly. But that's why I didn't draw it.
Yeah.
Anyone else have any questions? Thanks for that question, Daniel. Alrighty. Well, if y'all got nothing else, y'all have a great weekend. Appreciate your time. I'll have those grades in. You go ahead and upload it. I'll put them in like right now.
Thank you.